Okay, so yesterday, like, we covered quite a lot of things that probably didn't even make sense. Or did it? Rahima, how are you? How are you? So, okay, first of all, like, does any of us have any question as regards yesterday? Say maybe you went back, did some digging, found out some things that did not make sense, or probably maybe you didn't even go back to do any digging, but then you were reflecting on. So, like, did any question arise based on yesterday's class that you would like us to address before we start today's part? Okay.
Yeah, I think I while I was doing the implementation, it helped me to like understand what you were explaining, because when you were explaining about when you were explaining the whole part of like holding each of those steps, like the steps somewhere, I was thinking about, okay, maybe you're going to have something like an array for every computation, you push it into the array and all of that. So, but while I was studying how the hash functions work and all of that, I now understood that stuff you were explaining. So I even had to record the part where you spoke about it as on the 3 hour 42 minutes part of that recording. Yeah. So I just noted it down so that, yeah, because that's one of the parts that makes sense in the whole implementation of the Fiat Shamir. Yeah, so that makes a lot of sense.
That's nice. Okay. Any other person? Any other person, like any question, any contribution, like based on yesterday's class, maybe something you didn't understand in class, but maybe as you went back to look at it, it gradually started making sense. Maybe it has not fully made sense yet, but at least like there's some.
So the confusion between like evaluating at the proof polynomial and actually evaluating the polynomial, the next polynomial to evaluate at the point. Like when we explain that gave me like a bit of confusion where we take one variable and we skip one variable and evaluate at the rest. Then or when we get that value and claim some, we have to use that to get like a random value to evaluate them. So that's like that step basically was really confusing, but like as I was going through and trying to evaluate the steps, it kind of got clearer.
It got clearer. Did the steps we outlined yesterday, did they help in any way?
Yeah, they did. Sure.
Are you sure?
Like,
Be honest.
They were kind of black boxes at the end of the day, but the example I saw was pretty like detailed. So if you use the notes or the steps written down and the example, you kind of get it.
You'll get it.
I have a question though, because there's something I've been thinking about. I was thinking about, in our implementation, we did partial evaluation,
Yeah.
where you're partially evaluating at a particular variable. But now in the note, when we want to form a univariate polynomial, we evaluate over the Boolean hypercube, where we keep a particular variable constant and the other variables we turn them on and off based on ones and zeros. So I was thinking how to implement that because we didn't implement that stuff. So that's what I've been thinking about, like how would I go about implementing that, turning off, like, because I don't know if that is still partial evaluation, but I've been
Yes, it is.
Yeah,
But
yeah.
there's a faster way to get
to
get the value of A
yeah.
and 0 and 1.
So I've been thinking about it like, wait, how will I implement this part where you keep a particular variable constant and you evaluate the other one? So that has been on my mind, and that's like the major thing that is still making the whole sum check implementation kind of easy for me.
So if you write it down, actually, you kind of see the pattern where you definitely know that your answer is in very polynomial, meaning it will have 2 points. So those 2 points basically, how did you get them? So if you write them and you know that basically the sum of all the sum of the polynomial when is 0
Yeah.
and sum of the polynomial when is 1 will give you a particular claim sum. How do you now get those 2 sums? If you write it down, you kind of see
The pattern.
how to do it without evaluating at 0 and 0.
Sorry, that's a cheat. That's a cheat code. Okay, but what he said is true. There's actually like a pattern, right? So you don't necessarily need to maybe write a function that will generate all the possible Boolean hypercube values in the smaller number of variables, right? And then start evaluating your polynomial at those points. It's still implementation details. If you do it, it will work, right? But then, like, there is
When I have the cheat.
but then there is an easier way. Basically, you want to get a univariate polynomial, right? And basically, that univariate polynomial is, you can think of it in this implementation, because we're not working with multivariate, right? So we're working with univariate. So we need just 2 points to be able to identify that line, right? And getting the points at 0 and 1 is 2 points, right? Which you can use to get that straight line, right? So based on the whole sum check thing we've done, it should be pretty easy to get those 2 points, right,
Hopefully.
that make up the A line. It should be pretty easy to get those 2 points that make up the A line, right? Which is the evaluation. We want a line, like we want to collapse those variables, like the polynomial basically, to a line, right, that passes through, let's say, 0 and 1. So we basically need the evaluation of that line at 0 and the evaluation of that line at 1 to make that line. The way I said it is kind of confusing, but I don't want to I don't want to spill the answer. I just want people to go back and like just do some digging.
I'm sure it will be starting to come clear.
Yeah, it will. So I know that there are a lot of resources out there, right? Like, let's say the previous guys that have implemented these things, me and Wisdom's implementation, that are out there. Those implementation, I won't say people shouldn't go through them, right? But go through them only when you have made an effort. We can as well just go and make it private, right? Because we actually want people to put in some effort to think about this thing, right? So when you've put in some effort and you see that, man, You get. So you can then like do some research. So I'm sure there are still other implementations, not only like our own, right? But try to put in some effort first before like looking for an answer per se. Hope that makes sense.
Yeah.
The goal is to understand this thing, not just to like implement. Because if you implement and you don't understand, if you go for an interview and they tell you to explain, it's kind of like a problem, right? You like try to explain what you don't understand. They may just ask you one question that should be easy, but because you don't understand it, you won't be able to explain it. Hope that makes sense.
Yes, sir.
Okay. So um for the Fiat Shamir, am I pronouncing it? Okay. So let's see. How many people were able to like give Fiat Shamir a shot? I know it was like the explanation yesterday was kind of hazy, right? Wasn't really clear, but like how many people went back to just try?
Try to implement.
Yeah, try to implement Fiat Shamir. Okay. Were there any challenges you guys faced? I'm sure there were a lot, definitely. There were a lot, right? We can the two of you just like mention. I'm sure the challenges will have been close to 7, 8, right? Just one each. Yeah. Like one challenge.
Mine was basically like the bytes part and hashing. Those were the two major challenges I faced.
Okay, like converting.
Converting numbers to bytes, prime field to bytes and getting back the like trying to generate a prime field from those hashes we've created. That was like my major
Challenge. Okay.
Mine was basically like how to hold the hash like in an array so that at the end of the day I can return the entire array of all the
All
hash
the
and everything. Yeah. Like basically getting the structure of how everything is going to work. And also like my append, how will my append work? Is it like I'll push to the array like I was just struggling with that.
Okay. But any breakthrough on that?
Yeah, so while I was doing my research, I saw the update function from the Keka hash and all. So I was able to understand that okay, when you create a new hash, when you initialize a hash using the new associated function, what it does is that it creates a new hash and creates a state, an initial state. Now, anytime you call the update function on that hash that you have initialized and you pass in data, what it does is it adds that data to the state. So any incoming data that you pass gets added to that state. It's not like so that has the internal state of the hash function handles that already for us. So as you update it, it adds everything to the state. And also I get to understand that the order in which the data comes in is very important. For instance, data 1, data 2 is different from data 2, data 1, even if they are the same data. So it will generate different hash and also, yeah.
Okay, exactly. Yeah.
Mine was basically about like bringing everything together, actually implementing the structure it. The hash parts also gave some challenges. I used Poseidon, trying to find a good bucket that we use, a good crate. Then the types,
Type
Poseidon
conflicts.
case, and our own field, went from hack. Bringing everything together was like stressing me a lot.
Yeah. But Poseidon, I think it's Pedersen that works with groups. I've forgotten what Poseidon works with. I think Poseidon works with bytes, so well I've forgotten, but it's nice you tried Poseidon, yeah, because there are like different types of hash functions, right? There are the what's the name they call it? Well, there are ZK friendly hash functions, and like ZK friendly hash functions are functions that are hash functions that is pretty easy to write a circuit for for it. Pretty easy is not pretty easy. You know there are levels to pretty easy. Right.
For you, it's not easy.
No, not easy for me. Oh. But like those hash functions are functions that you is pretty easy for people that can do it. So write a circuit for that hash function. Right. So something like Kekak is not ZK friendly. Something like SHA-3 is not ZK friendly. But something like Pedersen is ZK friendly. You get? So SHA-256 is not ZK friendly.
So when you mean ZK friendly, what does it mean?
So that's what I was going at. Like I know we've not talked about like writing circuits yet. Right.
We are going to get there.
Your GKR replay is basically a circuit.
And we are going to utilize this Fiat Shamir and GPR, right?
Yeah, we use
That means, yeah, that means this haircut.
okay. No. Like Fiat Shamir, the hash function used in Fiat Shamir, it doesn't need to be like ZK friendly. You get? So there's a difference between using a hash function and like proving that a value hashes to something. You get? You can just use a hash function to hash something without necessarily like generating a proof that that value hashes to that thing. It's, okay, so let's say you want to build a Merkle tree, right? You need to hash all your leaves,
Yeah.
right? That's just basically like using a hash function, right? So another scenario now would be you want to prove that the hash of ABCD is equal to 8. So you're basically trying to prove that hash function takes an input and spits out an output of 8. Right. So in that situation, you now need to write the hash function as a circuit. We've not got into circuits yet. Well, we're going to talk of circuits. You get? So in that situation, you need to treat or write the hash function as a circuit. So basically, when you write the hash function as a circuit, when you now try to run the hash function, it's basically what we were talking about, like each step of the computation. So you're going to be keeping track of. You're basically like going to be keeping track of each step of the hash function and what it does, so that you can now like take that as a trace and then like use that to generate a proof.
Okay.
It makes sense now, right? So that's kind of like more internal. Yes, more internal. Okay.
Yeah.
So sorry. Like do what I say now make any sense? Let's say it don't make sense. So well, that's a question.
So there was something I tried to implement. There was something I tried to implement, like trying to make the Fiat Shamir generic, whereby if you want to like make use of Fiat Shamir, you can basically like set the kind of hash function you want to use. So I tried to make the new function to be taking in an argument of an enum type. I said to be maybe it's going to be like functions I want to implement. So I tried doing it, and you know, SHA-256 methods and KK-256 methods are the same.
Exactly.
So they are the same. But the thing was giving me one kind of error like that, and why? Because I just reverted it.
So it's kind of complex to go in that route because like not all implementations may have the same traits, right? So in order to go that route, that means you may probably need to define your own traits and then create a wrapper for each hash function. So in your transcript will need to now force that trait, right? And then like you now create a wrapper for each hash function, like wrapping it around that your trait, like create a wrapper for it so that it satisfies that trait that you have defined. I don't know if it makes sense.
Yeah. So I was saying like trying to like implement this trait for this particular hash function so that all of them will have the same function signatures.
Yeah. So like maybe SHA-3 may call it update, right? KCAP may call it append. Another hash function may call it another thing, may call it hash, exactly. So you need like a unified interface, you get. Then when implementing the wrapper for that particular one, you can now expose that function internally. Makes sense, right? Okay, so does anybody still have any question? Favor, you look like you have a question. Eh?
What else? Okay, the thing is, I wish we had the time so that we could do like the interactive.
Okay, the interactive
sound
protocol
check, so that we can now see how it differs from what's
from the non-interactive.
Yeah.
That I would love that. I get. Okay. Yes.
But do we have to rush into explanation of GK?
Don't mind me that yesterday. You get. I also wanted you people to. So normally like GKR is meant to start by next month, right? Yeah. So normally it's next week now.
Next week.
Yeah. So it's next week. So okay. I think that works. Right. Because it will help people to like get a clearer picture of what is like Fiat Shamir even doing. Like what is the transcript? What role is it even playing? Right. I think that makes sense. I think that makes sense.
So we could have just done the something before doing
You'll have done like interactive sum check
yes, before doing
before doing Fiat Shamir. But basically, we're going to look at Fiat Shamir today, right? Then we're going to review sum check. Then you guys would implement actually like that interactive sum check. There was a reason we didn't include it because we're thinking of time. Let's fetch sum check.
Do you think it's more work than Fiat Shamir?
Actually, Fiat Shamir is
Complex.
way no easy. Like after implementing the transcript, Fiat Shamir is way easier to implement. Just once you've gotten the transcript implemented, Fiat Shamir is way easier to implement. You get that it still works. So, is it okay with all of us? Let's implement the interactive protocol first, and then after that, we make it non-interactive.
Yes.
It's okay, right? Okay. Okay, so we'll be looking at the transcripts.
So I think they wrong with that. I don't know.
Okay.
I think I'm thinking.
Okay, so this is. So let's come back by. Huh? Let's come back by 10:45. Is that okay? Okay. So welcome back. Okay, let's see. Let's look at should we look at implementing the transcripts, or everybody wants to give it a shot? Let's look at it. Okay, so if you're for, say aye. If you're against, say nay.
For what?
So look at the
You want to
transcript.
write the implementation, or you want to explain?
Kind of like write it.
Yes. So I'm writing definitely.
Um,
Like write it in full or write it in pen.
write it in. So if you're for, just wave. Yeah, if you're for.
Yeah, for writing.
Yeah, if you're for right. Yeah, like let's implement the transcript. If you're against, if you're against,
So for
so I say if the people that are against don't want to make up their mind. So let's give it a shot. Okay. Really TypeScript.
I
Yep.
think it's correct.
Yeah. So picture the screens. Okay. Director something. Is there just one VS Code here? There's just one VS Code. Wait. It's well. Okay. It's painful, though, but life, that's life.
The mic was off.
No, it was paused. Yeah.
And you can take it again so that the people online.
Yeah. When I was trying to, like, I was not saying the VS code. So when I didn't want to just like keep the thing recording so that it doesn't make the video so long. Okay, so you're asking a question.
So I was saying at the end of everything, that's where
Yeah, at the end of everything, after the prover, like in the non-interactive protocol, right? After the prover has finished everything and generated the proof, he sends the proof to the verifier. Huh? Yes, to verify. Huh? To the verifier. No need for him to send the transcripts to the verifier, right? Because the same thing he used to generate the randomness, the verifier can generate. No. Like, this univariate polynomial will be in the proof, right? And we know that if we evaluate this univariate polynomial at 0 and 1, we should get the claimed sum. So if the verifier has access to this univariate polynomial, the verifier technically has access to both the univariate polynomial and the claimed sum, right? And those were the two things that the the prover passed into the function, into the hash function to generate the randomness. And the verifier has those two things. So the verifier can pass those two things to the same hash function and get the same randomness. Does that make sense?
Yes. So now, the prover, what the prover is sending to the verifier, that's just what I want to say. So he's sending the polynomial at every step.
Yeah, the univariate polynomial at every step.
So he's sending like an array of polynomial at every step that we took
Yeah, you can think of it that way.
to the verifier.
Yeah.
Okay, that's one.
Yeah.
What I thought was that it just sends like a proof, and that proof is just the end proof to the verifier.
Okay.
So now, this is like an array of just one proof.
Okay.
Isn't it, are we saying claimed sum or claimed sums?
Actually, like, anyhow you want to go about implementing it, right? But the idea is that the most important claim sum is that first claim sum, the sum over the Boolean hypercube, right? With the univariate polynomials in the proof, the verifier should be able to generate the other claim sum for the other rounds.
But it doesn't need to like compare.
He'll-
After like evaluating it at 0, I'm supposed to be able to compare to the one that possibly the previous.
He will still compare.
So you still need to send the claims on for every step.
You can just compare the polynomials.
He's
No,
comparing
let's
the
compare
claimed
the
sum with the sum of
The
the evaluations. Or should we go through some check again?
Yes, please.
Oh, this is So we have the initial polynomial, right? We have the initial polynomial. We sum it and we get the claimed sum, right? We generate the univariate polynomial, which is this. And this univariate polynomial evaluated as 0 and 1 should give us that claimed sum, right? After we've gotten this claimed sum, like the verifier now checks if it's equal. If it's equal, the verifier samples a random challenge and sends to the prover, right? The prover uses that random challenge to evaluate that initial polynomial to get a new polynomial, right?
Yes.
And then evaluates that polynomial, that new polynomial over the Boolean hypercube to get a new claimed sum. After getting a new claimed sum, he still generates a univariate polynomial for that new polynomial now, right? That the verifier will evaluate at 0 and 1 to check if it's equal to the claimed sum. Does that make sense? Okay. So he keeps on repeating it until he gets to the final check. So at the final check, the verifier does the oracle query at all the random values, right? And then the verifier, after doing the oracle query, the verifier also checks if that result gotten from the oracle query is equal to the last univariate polynomial evaluated at the last randomness, right? And if that is equal, the verifier accepts.
Sorry, can you say that line again?
Okay. So the last univariate polynomial, that's, let's say in our example, the univariate polynomial at C.
131C.
Yeah, 131C. The verifier will pick a random challenge, right? And evaluate that 131C as a random challenge, right?
So this is different from the C you get from the sample challenge from the transcript.
No, is it?
Is it?
Yes.
Okay.
Yeah, is it? So that's the non-iterative protocol.
Okay.
Yeah. So the verifier checks if that last polynomial evaluated at C is equal to the initial polynomial we started with, evaluated at A, B, and C.
That's oracle protocol.
Yeah, that is the oracle check. That is the last check basically of the sum check protocol.
So like this oracle, is it like a function that you're calling?
It's just polynomial or linear polynomial dot evaluate.
That name is too big.
It's too big.
Too big for it.
Yeah, it's just an evaluate function. Don't mind the big name. Okay, so I think let's just, this is 12 o'clock already. Let's just look at, so let's try and come up with something for the transcripts. It's so small. Is this better? Okay. So we have a transcript, right? We can, how should we go about it?
Hash function.
Huh?
Our
A hash
hash function.
function. Okay, let's see. Right? Right? So we need to implement the transcript. And on the let's have a function to create a new transcript. Right. Let's call it init, and it will return a trans.
Can we use cell?
Huh?
Like instead of using that transcript, can we use cell? We capture that.
Okay, here.
Yes.
Okay. Okay, right. Okay. So
What's different?
no, it's the same thing. Alright, let me add this to. So self is meant to take the hash function, right? Okay, that means when we're initializing, we need to pass in the hash function. Our saying is of type K, right?
We need to define K.
Yeah. Huh?
It's going to be
So generic.
Yeah, it's a generic. No, it's just a generic. So normally K is meant to be a hash function. We've not constrained that yet, right? So for now, it's just like a normal generic, right? Okay, so yeah, since we are using this thing, so right? So what next do we need?
We need a new function. That's what we need to do.
Function to generate the hash.
We need to append, right? Let's go like new, append, then generate.
Okay, you create a new,
Huh?
a new function.
Yeah, we create a new function. So we need append, right? Okay. So append should take self, right? And what we want to append. Let's call it data, right? Which should be, should use a vec or a slice.
Is it going to be a UX?
Yeah, bytes, a byte array. So, okay, so we want to take that value and we want to append it to the hash function, right? For now, our hash function is just a generic. So basically there is no method on the hash function currently. So does it make sense? So let's define, say, a trait, right, that our hash function should be forced to implement. Does that make sense? What should we call it? Hash trait. Okay, and it should implement append, right? It's going to be problematic, but okay, should implement append where it takes the data it wants. So let's just use byte array.
Is it the same thing?
Huh?
The way you wrote it from the way you're writing it, is it the same thing?
No, it's not the same.
What's the difference?
Okay, so one has like for a slice like this, you can't push to it.
What do you mean?
No, you can only insert values at specific indexes. So it's like a vector is growable, right? So you can push to a vector, right? But a slice is not growable.
So this is a slide.
Yeah, this is a slice.
Not growable. What do you mean by growable?
You need to first.
Let's say,
Not dynamic.
huh?
Not dynamic.
Yeah, the length or the capacity is not dynamic.
But you're not defining any length only at first. It's all you're trying to pass it.
Yeah. The same?
It's an array.
Hmm?
It's an array.
Yeah, it's an array. An array is
In
like,
Rust, array are fixed size. When you want to manipulate the size, you want to use vectors.
so I get what you say, like maybe putting of, let's say, 32, something like this, right? We can still do this, right? but it's going to be a problem because we are now constraining. So maybe if you have 5 gig of data, you now need to be cutting it into chunks yourself, right?
So then this way, that means we are just expecting just an array of one or
No,
An
An array of-
particular type.
an array of
any
bytes,
any
you it.
length.
Any
Yes.
But the reason why we are using this is because we are not manipulating the array. We are not doing anything
not
with it.
like-
That's
Yeah.
why we were supposed to manipulate it, then we make it operate.
Okay, so append, right? It shouldn't return anything. What should we call the other one? Should we call it hash? Hmm.
Sorry, Francis. I've noticed you and Wisdom like prefer using like traits as opposed to just like implementation methods.
Implementation.
Is there like the reason why or just
No,
preference?
no particular reason. Okay.
Isn't the generate hash going to be import into hash?
Yeah. No, the generator, after we finish appending, then the generate hash will now use what we've appended to generate a hash. Right? Does it make sense?
Yeah.
Okay, so we can restrict this guy now, right? And say you should implement hash traits. Hope there's not going to be a collision. Should implement hash traits. So implement hash traits. Right? And since we've implemented hash traits, then we can call hash traits. Like we can call any function on hash trait inside here. Right?
So traits are like interfaces into
Yeah?
I said traits are like interfaces.
Yeah, you can think of them as interfaces. Okay, so self dot, what do you call it? Hash function dot append data right
Still not saying.
to the trait. Eh? Yeah. So after it has accumulated everything with append, then it's when you call generate hash, that's when it does the actual hashing. Does it make sense? Okay. So actually this way we are going about it is kind of like a complex way to go about it. Right? But everybody can have their own different implementation. You get. So in this way, like we are taking the hash function, we are making it generic. Right? So we are not going to particularly see any hash function that would have these methods. So for any particular hash function we intend to use, we now need to like create another wrapper again. So that's like doing double work, kind of. Okay, so we have hash function. So now we are appending to the hash function. The hash function inside here. That's what we're appending to. Does it make sense? Are we sure? Yes, this dot append is from the trait, but we are calling it on the hash function, right? Because we have already said the hash function should be of type k, and anything of type k must implement the hash trait.
Okay, what you're basically doing is like you're giving us a generic implementation of what it will look like. So by using the hash function, basically the hash function trait is will have the functions you want to use. So this hash trait is like a mental picture of what the hash function will look like.
Exactly. But different hash functions are going to have different functions. You get, and us doing it this way means we cannot just use any hash function.
Yeah.
If we want to use any hash function, we need to now create a wrapper of this trait for that hash function so that it will satisfy this hash trait before we can use it. Now we are going to be doing something with Kekak. We are going to create a wrapper, right, so that we can see what it's going to look like. But does everything make sense up to this point?
Yeah, except the fact
Okay.
this hash function, I get that the dot append is from the tree.
Okay, shall we change this name?
No, like
We can change
I feel
it.
like this function.
They are different.
I get, but then I feel like this append function is supposed to implement, like, do the real append rather than calling the one in the trait, which is just like the function signature or something.
Yeah,
So
it's
where
meant to do the real work, but we are not the one doing the work. The actual hash function implementation is what is going to do that work. We are just creating a wrapper.
That is like temporary.
Huh?
That is like temporary.
Yeah, you can think of it.
The actual package that will be-
Yes. Is it making sense?
Yes.
Are we sure? Okay, so we have. Should we change this function name
Yeah.
Yeah, to prevent confusion.
to prevent confusion? So what are we going to change it to?
Absorb.
Absorb. Okay. So we are good, right?
Yeah.
Okay. So after absorbing, we want to generate a random challenge, right? No, they are two different things. They are totally different. This one is specifying that this hash function needs to implement this trait. You get? While this one is on the transcript itself. I hope I'm not confusing somebody.
It's just
Huh?
like that field listing and
Yeah, just like the field one,
But now
where the
we are
prime
creating
field was.
something.
Yes. Okay, so what is the next function we need?
Squeeze.
Let's call it squeeze, are we?
Yeah.
Okay. Is it double E?
Yes.
So it takes self, right? But this has to be mutable, doesn't it?
Yeah.
Because we are mutating the hash function. Do we agree? So squeeze just returns a byte array, right? And okay,
I thought like this quiz is supposed to include like just one, not an array of
okay, you want it to return a field element,
yeah, maybe
right?
like
Okay, so let's return a field
or
element.
bytes.
So you can return a byte, then we can convert that byte to a field element, or we can just do the conversion internally. You get? So okay,
No defined field.
yeah, we've not defined field yet. So we will need to define a field. And it has to implement prime field, right? Transcript. Do we understand what is going on?
Okay. What's wrong?
I can think of phantom data as a placeholder, right? Maybe you have a type that you're not necessarily like instantiating in the struct, right? So if we had, so we defined a type here f, but we are not using it in the struct, right?
Are
You
you
get-
not going to use it?
Yeah, because we are returning.
If
You get. Another way to go about this will be, okay, we remove it from here, right? And then we tag it specifically to the function that we want to use it on, right? So here we'll be using exactly.
Sorry, I have a question based on this introduction. That data,
Yeah.
you said you can actually pass in, you can actually pass in our English polynomial or the Epson, right?
Yeah.
But that data is just like an array of U8, right?
Yeah. So we should be able to convert, what it technically means is that we should be able to convert our univariate polynomial to bytes. And we should also be able to convert our claimed sum, which is a field element, to bytes.
You know, like, I don't know, you know, our polynomial now is going to be like, in its evaluation form, it is more like a vec of, that stuff. Is it going to, can you pass it directly into this? I don't know if I'm
You need to convert it to bytes. You know, because it's an array of field elements. So in that array of field elements, you need to go through every element in the array, convert it to bytes, yes, and append. Does that make sense?
Yes,
Does anybody have any question up to this point? Any question? So should we go with this, or we should go with should we go with this, or we should put it basically on the transcript?
I think this one is going to understand.
This one is going to be painful to use in code. It's going to be painful.
Yeah.
Huh? Yeah. If we want to go this way, it's going to be very painful to use in code, because anytime we are calling this, we need to yeah, we need to use the angle bracket. Okay. But do we understand? Huh?
What are we putting? What are we doing?
Like this prime field here.
Yeah.
So we are saying, should we leave it on the function, or
Okay.
we should put it on the transcript so that we don't have to, like, once we put it on the transcript, everything within this scope will have access to it. Yeah.
Transcript is better.
The transcript is better, right? Good. Okay, so to put it on the transcript, we need to specify here f prime field, right? But if we do it this way, we are defining something that we are not using in the struct.
But it's not complaining.
No, that's because I have not saved.
Oh.
Yes. So it's complaining. Consider removing it, right? But we actually want it, right? So we use this phantom data as a placeholder to hold the type, even if we're not necessarily using it in the struct.
You can use options.
Huh?
You can use options.
If you use, yeah, you can actually use option.
Option.
Hmm?
How is it?
Option, like right. So it can either be a value or none, right? So option still works. You get. But let's use phantom data. Okay, so we also need to specify it here, right? We need to specify Does it make sense?
But this phantom data, is it dummy data?
Yeah, you can think of it as dummy data.
You have to specify that on type.
Huh?
You
Yeah.
have to specify it use type.
This is a value, not a type now.
What's it?
Right? We are saying for the field key, use the value phantom data. So it's just a dummy data. It stores a type, blah 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 blah. You can learn Rust to this thing, you know, have it? Yeah. I think that was how I learned Rust. This guy showed me. Okay, so does it make sense up to this point? Are we sure? So we want to squeeze, right? And I want to just call our hash function generate hash. Yeah. So let's convert it to a vec. Yeah. Since the size, generate hash is just returning a byte array. So Rust doesn't know the size of the byte array, right? Because we didn't specify a size here. If we specify the size here, let's say 32, then it will know the size so that when it's allocating memory for it, it knows like the amount of memory to allocate, right? But since different hash functions, like some of them may return like maybe 256 bits, some of them may return like 64 bits, like different hash functions have different output size. So that's why we're just like making it a byte array, right? Then when we come here, we say, okay, you've returned a byte array, right? And rows don't necessarily know the size. So let's just basically make it growable. Let's put it on the heap, right? So we just make it a vector. No, a vector is stored on the heap, right? No, we're not done yet. So we've gotten this. Yeah, we now need to convert it to a field element, right? So, on our prime field, we have okay, as from random bytes, right? Or okay, from bytes from big endian bytes mod order. So we go with big endian and little endian.
What is Ellie?
Big endian, like B is big endian,
What about Ellie?
L little endian.
Okay,
Yeah. So yeah, hash output. I don't know the value of type is the size of okay, because this is a reference, right? I'll just clone for now. Wait. Okay. Now be statically let's make it still statically determined. Yeah, I cannot. Okay. Okay. I need to specify the type. Let's see. This takes in an array of UHs. Okay. So you can basically just pass let's see. Okay, self itself is we're taking a reference to self. Yeah. Okay. I don't want to clone here. Okay. This.
We're not converting into a verb.
Yeah. Well, I can still convert it to a verb, but that's not like the solution. You get. Cannot be statically determined.
Sorry.
What if you make what's the returns? Generate dash. Why you make it a fixed like that, like add
You know, like we're making this thing generic, right? So the generate hash, the different hash functions are going to have like there are different the different sizes of output. So if we constrain this, that's like putting a constraint on the hash function, right? That's putting a constraint on the hash function, which we don't want to do, right? So okay, let's see. Let's make it a vec. Alright. No need for this. Alright. So after we get the hash, we convert it to a field element using this from big int byte mod order. Does anybody have any question up to this point?
How did you fix the
No, we just made this made it to return a vec instead. You get. Does anybody have any question? Are we sure?
Are you think we are not using that field element? This from being Indian bytes, order. It's from the field element.
Yeah, it's from the field. It's from the
What
prime
if
field.
we are using our normal weights? Like for wanted to remove wanted to use the weights. So
Like if we want to use the U8 here,
yes,
we can still do that, right?
does it implement this method?
Okay, no. If we want to use that, then after we've gotten that hash output in our code, we are now going to convert it to a field element. You get? That is in our code. Well, does it make sense?
Yeah.
Okay, does anybody have any question up to this point? Does anybody have any question up to this point? Okay.
Is this function is where you hash, you convert it to the byte.
Yeah. This squeeze function is where we do the squeezing, we get the hash. Yeah. So after we get the hash, this hash squeeze is returning a field element. So the hash is usually an array of bytes. It's a byte array. Right, that is what a hash is. So we need to now convert it to a field element so that the prover can use it to evaluate the polynomial. Right. So we use this f from byte mod order to convert it to a field element. Yeah. So this function returns a field element. Does it make sense up to this point?
Yes.
Okay. So we have our init, we have our absorb, we have our squeeze, right? Okay. So, but then to use this, like, let's now instantiate, or let's now like create a wrapper over a concrete hash function that we can use. Okay. Because here we made the hash function generic. We made the hash function generic, and if we want to just use this straight up in our code, it's going to be problematic because there's basically no hash function. Everybody are implementing the hash function. What is their business with you, right? And then you're putting restrictions that my hash function, any hash function that is used here should implement, append, and generate. Who cares? Like, the people implementing those hash functions, do they even know you? Like, they don't know you, right? So how would they like conform to your own restrictions? That's a problem, right? So to solve that problem, for every hash function, like, these people, they don't know us, right? They implement their hash function, but us, we want to use their implementation. So we need to make their implementation to conform to what we want. Is it making sense? Okay. So I'm just going to do like an example with Kekak. We just create like a wrapper for Kekak. Okay. So let's first add it. So SHA-3 is a family of hash functions, and Kekak is one of. Huh? You can. You get. So that's why we made it generic, so that you can use any hash function. Okay, so we've added SHA-3. Okay, so we need to bring it in, right?
Where is that phantom data?
Huh?
Phantom data.
The phantom data. This is where we use it in the field.
Wait, what is it?
It's just a dummy type. Huh? It's just a dummy type. Like when we added this field elements here, we had two options. Either restrict this function to, like, either define f particularly for this function, or define f in a way that it can be used by, say, any other function. Say if we want to add any other function to this transcript that would return or use a field element, we don't want to start like adding that field element to each of those functions. We want everything in the scope of the transcript implementation to have access to the field element, right?
So that's what we did now when we added it to the implementation.
Yeah, that's why we added it to the implementation. But adding it here, when you defined struct, it was not there, so it doesn't know what it is. So you need to tell it what it is, right? And if you just tell it without using it in like in the struct definition, it's going to complain that you
Just define
define the type without using it. So that is why we now use like phantom data.
Couldn't you have just done it without the phantom data? Just calling
F. That means you now need to like, we can still do it like that.
But what is the trade-off? What makes it necessary to use that?
To do that, like we'll now need to like pass in a concrete like implementation of a field when we're also creating, when we are initializing.
Like that FQ?
Yeah, like FQ. You get? And like it's not something maybe you may like it, but like passing in FQ anytime we want to, it doesn't.
When we use primary in our very example, we didn't use FQ inside it. We just use F and everything works. When we're testing, we have to use FQ. So why is this one? Why do you have to use FQ here?
Okay. Let's. Oh, what are you asking? If we use F here like this,
Yeah.
right? Okay. So that means we need to take in F in this function. This is a concrete, it's returning an instantiation. It's returning an instantiation of a transcript. So it needs a concrete value. I don't know if it makes sense. Here we are passing in a concrete value. Like it also needs like a hash function, right? So here we are passing in that concrete implementation of a hash function that we can use here. So if we want to do it that way, we will need to also pass in a concrete implementation of a field that we can use for the field. You get? Then any other place in the code, you can just be calling like F blah blah. But this now is where we are creating like a concrete
Are you passing it
transcript.
inside?
Yes.
So when we are testing, we don't need to pass anything. It automatically does it.
Yeah.
What we're just passing is just the hash function.
Yeah, just the hash function. Hope that makes sense. Okay, so we're going to bring in Kekak, right? Okay. So we want to create basically a wrapper around Kekak to make sure that it conforms to the traits we have defined. So we basically need to implement hash traits for Kekak. Does that make sense? Like for this Kekak we brought in, please, is everybody following? Are we sure?
Yeah.
If you have any question, please. Let it not be like we're just rushing and like not everybody's following. Everybody's following, right? So we brought in Kekak. Kekak has its own functions, right? But we want to be able to make it conform with hash traits, because we have already like restricted the hash functions that can be used here, that they must implement hash traits. So we now need to implement hash traits for Kekak so that it will conform to our to our traits we define, right? So let's just use this young man. So we need to implement these two guys, right? I think this is where the major problem comes. So we have append, right? Um, wait, I thought append was. It should be mutable. Okay, so we need to actually create a Keka wrapper. Does this make sense? We're creating a Keka wrapper for Keka 256, right? So basically we can now implement that on like the hash rate for the Keka wrapper instead of for Keka directly.
Why
Right.
like the difference?
It's because to we want to like we want to be able to keep track of the Kekak's internal state.
Okay.
I don't know if that makes sense. We want to be able to keep track of Kekak's internal state. So if we didn't do this Kekak wrapper, right, and we just use Kekak here, if we are calling, okay, a self should still work, right, for Kekak, right? Smart stripes. So that's but like there's no concrete implementation for Kekak that we can call a function on. I don't know if it makes sense. Like we're just implementing the hash rate for Kekak, right? But there is no, if you want to hash something, you need to do like a Kekak implementation, like column, say updates or something like that, right? Well, let me just continue. It will make sense while we actually went this route to implement this, right? Kekak wrapper. So to be self dot Kekak dot
So this update comes from the Keka.
from Kekak, yes. Um, okay. So we need to bring in also digest into scope.
Why digest and not update?
Like the update function, I think is implemented on digest. I'm not exactly sure. Oh, yeah. So let's come on, let me verify something. Okay. Okay. I think like this still works, right? So yeah, this still works. I think let's just use Kekak, right? Let's just use Kekak instead of using the wrapper, because the wrapper is now like creating another layer of depth. Okay. So provide the arguments, data. Right. So we're just calling this update now on Kekak 256, right? Kekak 256 dot update, and we're passing in the data. Does it make sense? Okay, so after we append, we now need to like generate a hash function. Yeah, I removed the wrapper. So we now need to like let's store it somewhere first. See what it returns.
So finalize is the method on which after hashing.
Yeah, like after doing all the appending, so finalize does the actual hashing. Like with all the data you've appended, it will now do like, you can think of it as like doing the squeezing, right?
It's something about
Yeah, because we are not returning anything yet, right? I wanted to see the type it returns, the finalize function.
if you remove the semicolon, it might tell you that the return is different from
Yeah,
expected something.
it's real. Yeah.
Yes, so
So expected. But this is what I found a generic array, right? So that is just like for the hash function. Or we can just use dot to vec, right? Oh, that thing so should still work. Let's stop trying. So it's not that expected. Okay, then unwrap. Yeah, let's just use the dot so vec. That's it.
I was saying if you can make it return an array of U8 instead of
a vec.
Yeah, we removed it because we had issues at home. We changed it because
was giving an error that time.
Yeah.
Uh,
But that's the traits. Let's see if it works, right?
The issue was up
Yep,
there.
up there is now.
Yeah. You cannot know the size at compile time.
This was like
You asked
Yeah.
similar to the error.
okay.
But you don't want to make it big.
Okay, you don't want to make it.
Yeah. But my old daughter
I
is
see.
not Jewish.
Yeah.
Yeah, that's a very didn't actually.
Yes.
Yep. That's a very actually does it. So we're taking like a reference to self, right? I think not finalize or to very consumes, right? So
Is this supposed
Can I
to be
clone
a
it?
table?
hmm?
Can you not mute it?
Yeah, clone will.
No, we're not. I'm just generating a hash, right?
Yeah.
Clone works, but
Not
no, there's one thing about like in production, if they see in short, like all these senior devs, if they see clone, like they hate seeing clone.
Spoils
Why?
memory.
Yeah, because when you clone, you're making a duplicate of something, right? And you're using like your system memory. So just imagine that you're working over like 5 gig of data, and then you cloning, you have made it 10 gig, right? So maybe you're in a for loop and you're looping over an array that is 5 gig, and say you're not doing that thing like multiple times. That's crazy. Like your system will just hang. You get. So most developers don't really like using clone. Like some of them, once they see cloning or this thing, like they just why this guy doing. Sometimes you can't avoid it. In this case, it's avoidable, but for now, let's just stick with this. You get. So
It's like any TypeScript.
And yeah.
Is it any?
yeah. Okay, so with this, we can now use like, but there's still something, right? This will work, right? It should work, but okay. I think my fear is not necessarily because finalize. I think there's finalize and finalize reset. Right. Yeah. So if you finalize, you're just squeezing. If you finalize reset, you're squeezing and you're resetting, which we don't want.
Yeah.
Right. Yeah, which we don't
You
want.
don't want to reset it.
You don't want to reset it. You want to keep building on top of it. Yeah. So I think this should work. So does anybody have any question like based on what we've done so far?
So like this generate hash is going to be working on an array or a vector. Like the what's it called? The data passed to it is going to be an array.
The generate hash or the
Yes.
append?
Yeah, from the append, the generate hash takes like data that the append has already updated.
Accumulated. The accumulation is happening in Kekak's state.
Yeah, but it's going to be in array form. Because I'm wondering
Yes.
why this generate hash is going to be giving us an array.
Why generate hash is giving us an array?
Yeah.
Okay, no, it's just bytes. It just returns bytes, not necessarily an array. An array is the way we can visualize or the way we can look at bytes. We need to give it a structure.
Bytes
Right.
in an array.
Yeah?
Like bytes.
Array of bytes.
Yeah, an array of bytes.
So
Yes.
is it going to be equal to the number of data in the previous
No. No, it's not going to be equal. It's like this generates hash. It just generates. It's just like when you want to like hash a value, right? You pass in data and it returns the hash. So that hash, you can think of it as bytes. It returns bytes, right? And one way to represent bytes in programming is by representing it as an array of U8. You get, because one U8 is a byte. One U8 is made up of 8 bits, and 8 bits is 1 byte. So that's just how we used to represent it. It's just a way of representing, just a way of representing a byte. So a byte array now is now like a collection of bytes. You get?
DK was also saying that there is a byte type in Rust. So I looked that up. There's no byte type in Rust.
It's not.
Or you
I
have
think
to use
it's
like
you need to
factory.
import. I think there's a library. Yeah, there's a library that does that byte array. Yeah, I think you can also use that. You can also use that. The idea is like having a byte return. I should be able to now convert that byte to a field element. That's what is important for us, right? So basically, like if you now want to use a different hash function, like maybe SHA-256 or something, you can still implement the hash traits for that SHA-256 and then use it, right? So does that make sense? We didn't really do anything here, right? We're just wrapping somebody's Kekak implementation with just 40 lines of code with plenty of spaces, right? So when we say transcripts, this is it, right? It's just a hash function. We're done. Just a hash function.
What?
So can you explain how the implementation for Kekak works? Because we had the trait already. And now implementing that trait or something else.
For Kekak.
Append the code in the original implementation. Now which one does it take?
So when you call like this append, it's just a trait, right?
Yes.
Which one?
Yes.
This one. So it's going to call the append on the
Depending
on the type. Yes.
So in this case, what would you pass for that key?
For this key, you pass Kekak. Yeah, you pass Kekak. So let's test, right? But does everything we have done make sense up to this point? Does anybody have any question? Does anybody have any question?
Not
Okay,
like
again.
explanation, like the next thing I spoke.
Okay.
The thing is because I don't really understand like finance fields on my own, right? I don't understand this phantom data.
No. Phantom data does not have. It has no business with this guy. right? We can as well do C, right? And just the phantom data T. Anything it is. It's just a placeholder.
Or if you want to use any kind of a certain function, but when you want to implement kind of you have to implement it in the structure to use it in the implement. But when you want to create a new function of the kind field, you don't want to actually differentiate that you're using kind field everywhere, so you just put like a placeholder for kind field there. So that when we are creating like a new transcript, you don't need to actually manually put in a kind field. Here will just allow it to just go through. Since I already put it underscore field as phantom data, it will not ask you to pass the kind field, it will just ask you to pass hash straight directly. Yeah.
Does that help? So it's just like we're defining a generic. You know what a generic in Rust is, right? But in the structs, we don't have any need to use it. You get? So it's as easy as us just removing it, right? You get? So there's no need for it. If you're not using it in the struct, there's no need for it. You get? But because we want this because we want all the functions in this transcript implementation to actually have access to that F. The only particular function, okay, we've removed it here, right? Okay, so we can also remove it here, right? Then here, let me remove this. Let me remove it. So we did not use F anywhere here. We did not use F anywhere here. But we need F here because we want to return a field element, right? We need F here because we want to return a field element. But now the program doesn't know what F is, right? We can decide to now define what F should be here, right? But if we define it here, that means only this function will know what F is. You get? So if maybe we want to later put that this function should actually still return F, this function will not know what F is, right? A way we can do it so that this function can know what F is, this function can also know what F is, like all the functions, is to put it on this scope, on the implementation block scope, so that all the functions will know what F is. That will now force us to use F here, right? Us using F here, that means it's a different signature from this word now. Like these two things are different. You get? So we also need to like specify it here so that both of them will have the same signature, right? And specifying it here, you see, we have come back to that problem, right? We don't need it here. We don't need it when we are creating a struct type, like a transcript type. So in order to like just accommodate it, you get, we can now use this phantom data. So that phantom data is just a placeholder. Yeah, you don't necessarily need, like you can basically just think of it as dummy data.
If I want to hold data, I use phone.
Yeah, if you want to like hold like a dummy, yeah.
So,
Or should I say dummy data or dummy type?
okay.
Yeah, dummy type.
Does the update function automatically update that field?
The update function,
The keka.
the keka.
There's the append.
Okay, this append.
Yeah.
It takes this. It takes in the data,
And updates it.
yeah, and updates its own. Wait, which are the field are you talking about?
Yeah, no, what does the update method? What does it update?
It updates the kekak's states. In kekak implementation, like if we go to the kekak implementation, right? Man, let's go this. Scary. Right. So if we go to kekak implementation, kekak has is.
Your past is up.
Are we sure?
Somewhat
It's in more
state.
states.
Okay. So like basically all of them have like a state. You get like both Kekak, SHA-3, like all of them, they have a state. So when you update, you're just modifying the state, adding randomness. Right. Then when you call finalize, that's when you actually do the squeezing, like you generate the hash. Does that make sense?
Yeah.
Are we sure?
Kind of like giving you a chance to contribute to the randomness that's
Yes, that Kekak, yeah. So anytime you're updating, you're just adding to that randomness, adding to the randomness. When you like finalize, you generate based on all those accumulated randomness, you generate a random value. That random value now you need to convert it to a field element. Does that make sense?
Final question. So that field element in this entire implementation will not be the random variable
Challenge, yes. The prover will use. You know about it. Okay. So, are we okay?
Yes. Yes, yes.
Are you sure? Are we sure?
Well, I'm having a question on the down.
Okay.
This like now. So my doubt is that this keka,
Yeah.
this keka we are using now,
Yeah.
like are we using it anywhere in the hash function?
The kekak.
Yes. Or I don't know.
Yeah, we are. I'm coming. Sorry. Let me correct this stuff. Okay. Yeah.
So sorry. Where are we using it in the hash function?
This is it. You get like this is a trait.
Yeah.
We are defining a trait on a type. So defining that trait enables us to call that method. Right. So whenever we call this method,
Yes. But the hash function, I thought the type would be keka, or I don't know. I'm just
which hash function? This hash function.
Yes, he said whenever we call this, right, it's going to, like, if we go to that trait implementation, well, like, I don't know. I'm not seeing I'm not seeing
The link.
Yes.
It's because like we're implementing the traits for Kekak. You get what we are doing here is just defining the traits, right? So anytime we specify k here to implement this trait, k here is a hash function. You can think of k here as a Kekak, which is basically this guy.
Yes. So can you please scroll down?
Up or down.
Okay. This no, can you go up? Okay, we define the traits. Then show the implementation of that trait is now in this spec right?
Yes.
Okay, I think I
Yes.
get it now. I think yeah.
It's clear now,
It's
right?
clear now.
Guys, are we good? Hmm? I can see you. Feel like I keep making noise. Okay. Yep.
What is this?
Oh, we did not. Okay.
It's like it's testing some other.
Yeah, that's like the univariate. This that univariate. Yeah. Okay. So what are we doing? What do we want to do? Are we following?
Yes.
Are we sure? Okay. So what to initialize a transcript? Right? And it takes a hash function. So let's bring in you have a question. socialize this stuff again. What is that? Yeah. Let's also bring in the hasher. Okay. Yeah. Research the field. This is what field hasher. That's field hasher for Kekak. Right. Say domain what is this? Class type expected array of units. Okay. Let's say that is domain 1, right? Okay, so we can see here that it's complaining already, right? It's complaining already that Kekak does not implement it. Okay, the trait bound this or this or this hash traits is not satisfied. You get. So this hash trait is not satisfied. Is that what they are saying? That is not satisfied for Kekak. So we can't use Kekak directly, right? Because we have not implemented the hash traits for Kekak directly, right? So what we need to do is I think this should be it, right? For Kekak. Seems it's still not seeing it. Huh? Okay, the trait hash rate is implemented for this. For core wrapper of Kekak, not default field hasher.
Where is this default field hasher from?
No, like it's just basically like a generic. So I call it generic implementation of a hasher, right? So we can now pick like a particular implementation, say KECAC 256 now, to use it on. I call it. So it's a generic, just a generic implementation of a hasher. So we're now specifying like KECAC 256 for it to use. Let's rush.
Do we need to, like, is it compulsory you need to initialize the default hasher with like a byte value?
Wait.
A byte value. Like, while doing the default field.
Yeah,
you
that
add
is.
one stuff.
No. You can use anything here.
Okay.
Yeah. So this is just like it's the interface, the way the interface was.
Okay.
Yeah, the interface of the default field hasher. You get. So it can be any random number, I think. Yeah.
So does that mean that once you like write the first value basically overrides what you initialized it with?
No, don't think of this. You can think of this as like adding randomness.
Okay.
You get initial random.
Can I see the wrapper, the implementation of the wrapper?
Of which one?
That's default field hasher.
Okay. So this new
Okay. Makes sense.
makes sense, right? So is anybody lost? Huh? Is anybody lost? Where exactly?
These are the
No. Where exactly? Like is it the test that you people got lost or say before we got to the test? Where exactly?
Before you say you were having error.
Error. No, those ones were those
How was it I got lost?
you know, we changed some when I was trying to explain something to Favor. We removed that. Yeah, we removed the F, right? Yeah, so that was why those errors came. So I just
To explain. Yeah, but I think the part, can you scroll? That's when you're trying to implement the trace for the Kepler. I think that was where, yeah.
okay.
So please can you go?
Wait, sorry.
So this now, can you just explain it?
Okay. So we defined a trait, right? We defined a trait, append, and like hash trait that has the functions append and generate hash.
So the reason why we're doing this is so that any hash function that's passing will have this tree. We're forcing it.
Yeah, we're forcing it to have this trait. But then, like KECAC doesn't have that trait, right?
That doesn't implement this.
Yeah, KECAC doesn't implement this trait that we're forcing.
So we want to make Kepler implement.
Yes, we want to make KECAC to implement it. So that's why we now did this. Implement hash trait for
So that
KECAC.
if you had more traits, like maybe that Poseidon about it.
Yeah, we need to now implement hash trait for Poseidon, hash trait for SHA-256, and on like
So
that.
that self there, that is the Kepler itself, right?
Yes, this is the kekak itself.
And it implements that update.
Yeah, it has the update function. So we are basically just creating a wrapper for this.
So everything
Okay.
gets like aligned with sort of like an interface on.
Yes, which is the hash interface that we define. That makes sense.
Yeah, can you go up, please? Go up. Yes, yes.
Yeah.
Okay, you are calling that hash straight that you.
Yeah, the hash treat.
Yeah, it's
But you know,
the one at the down.
yes, that one down. But you know, like when we call this append, internally it calls kekak update function.
Yes. Yeah. So you are just calling that append.
Yes.
So what if one has a function like that initializes a struct where the initial struct value is a new kekak instance, and then you for update for append you just call that. Sorry, can you go down? And then for yes, for append you just call this update on it, and then for generate hash you just clone it and finalize it to work just like that. Will that still work well?
Yeah. But like, just repeat your question so that I'll be sure
What I'm
that.
saying is now, like, I have a struct that initializes a new kekak in the struct. Like
Okay.
kekak,
Yeah.
new,
Yeah.
just that. Then I now have two functions. One function is append. Now that append just calls that self dot update, passing in that data, that UAT data to update
So that's
that
yeah.
already initialized
kekak.
kekak.
Yeah.
Then when I need the hash, I
You just call it directly on the
self
kekak.
clone, then finalize, then to fed,
Yeah.
then to vec.
It
That
works.
would work, right?
Works. Any other question? Okay, so let's go back to our battle. Hmm. I don't know what this guys. Okay. Okay. It's implemented for core. So by default. What this guy is complaining when it's shouldn't, right? No function associated. Oh. So it's still that digest, right? Okay. So we need to specify the type. So it was basically that digest. We did not import it, that was why it was throwing that error. Right. Okay, so for the hash function, it's for hash traits. It's not satisfied. Oh. We didn't specify that this should implement hash traits, so why are we getting that? Okay. By the transcript. It's not. Oh shit. Oh why? But as a prime field, shit is not satisfied. Nice. Well done. something right. Let me. Let me just verify it. So.
I'm seeing trust. I'm seeing smart.
Right, test.
Then it's a dream job.
Okay. That's why I use that stuff. Oh. I shouldn't steer you on there. Or do we mix it up somehow? Looking like it. Okay. Let's just define. I'm coming. Let me just define a hasher trait, like the wrapper for the kekak. So I can use the wrapper. I'll need to pass the wrapper.
Pass the checker. So everything is the same, just with one minor detail.
Yeah, so need to implement new for the keka wrapper too. Okay, define it says so. No need so.
What if you initiate it inside the test?
No, no need. Let me just implement keka wrapper. Yo. Using constructor. Okay. Transcripts needs It's like a proper. This guy is still complaining. Still complaining. Shift is not implemented for Kekak.
You can initialize Kekak 256.
Huh?
Kekak 256.
It's Kekak new, right?
So sleep. You said that. Okay, I'm doing it out here.
Yeah. Like. I mean, so this Kekak 256 new. It's still complain though. Yeah. That's implemented for Kekak wrapper.
Because that line worked here.
Huh?
That line.
Or is it the
But I'm not using the
spelling?
record.
Which of them?
The one you just wrote. But I'm not using the record.
Okay. Coming. don't know why it's I'm definitely not doing something right. But
What's in front of this? Scroll.
hmm?
The African device. In
Yeah.
front of transcript.
In front of transcript.
Yes, the first one in front of transcript.
Which one?
No. Right. Yeah, the one,
This.
yes, that one.
Yeah.
I don't have all that.
Like it needs a type. If not, it will complain. It doesn't know the type per
Okay,
se.
leave
You get. So it doesn't know the type. Cannot satisfy
mutable.
underscore prime field
Is that
or I'm not sure it's about mutable. It's not about mutable. It's mutability. It's just that type definition. Right. Wow. Almost there. Oh Lord. Okay. Okay. So yeah. It was just like the type. I think I was switching it like I put FQ yeah before so no, it's part of those things. So now we have our transcript, right? And we want to append okay, it's absorb we called it.
Yeah, put it absorb. So you have to do that and also absorb.
Let's call this boy, right? Boy has bytes. Okay. Yeah, this has to be mutable.
I need to do
Alt
Alt Z.
Z.
Alt Z to wrap with stuff. So you want that to.
Oh.
I mean for VS Code.
For
For your VS Code, like because the line is extended.
it's long.
Yes,
Okay.
so you should do Alt Z to wrap it.
Oh. Thanks. So we absorb, right? Boy and girl, right? Then now let's sample. Let's challenge transcripts. What was the function we used?
Squeeze.
Is it squeeze?
Yeah.
Sorry, transcript dot squeeze. And it will return a field element for us. Right?
Yeah.
So let's see the field element.
So we print. Yeah.
Okay. And let's see what we get. Okay. So this is our random challenge. So if we should run this again and again, we're still going to be getting this same random challenge, right? I will pass in boy, we pass in girl. We're still going to be getting the same random challenge,
The same.
right?
Easy understand.
Is it changing?
Yeah,
Yeah, 3 2 3 1 3 2. Right. 3 3 2 3 and 3 1 3 2.
Sorry,
But
what did you do to display the chart? Mine is not displaying.
It's not displaying.
Just let me see.
GBG.
That's the same thing I did.
But you need to use like
No
yeah
capture.
dash no capture.
Okay.
Oh,
Additional capture means-
like the that's no
Then dash no capture. I don't know what it means. But you can use it to like if I want to think of it say just normally, I'll expect it to be capture instead of no capture, right? Because these DBGs, when you run your test normally, it doesn't capture them to display the debugs, right? So, but when you put the no capture there, like it's now, it displays the, like any debug you have in your code, it's going to display it. So,
Your squeeze function, you do need to return the field element.
yeah, I made it to return a field
Mine
element.
is returning an array.
Okay, an array of bytes,
Yeah.
right? Yeah. So we made it to return a field element. Yeah. So after we got the the hash, we converted it into a field element, right? So okay,
For this, the test part,
yeah.
can you give me, like, why could you access the squeeze method with dot squeeze and then the init method is using the column?
The init method is using the colon, right? That is because when we are initting, we are creating a new instance. So there is no prior instance. You get? So when we init, we create a new instance. So when we are now calling absorb, it's on that instance that we are calling absorb and squeeze. So that's why like we're now taking self, right? If you see the init function, it doesn't take in self because there is no self at that time.
Yeah.
So it's after you've initialized that we now get something that you can now call yes self.
So the way you pass your transmitter as
Which one?
your tests.
Okay.
Yeah, but I think another way to write that like supposed to be in front of the quotes.
Okay, be in front of the quotes,
Yeah,
right?
remove the dot as
Instead of yeah. Would that be is that not binary? It's be not
No, no
binary.
That's
Huh?
bad.
That's bytes.
Yeah.
Oh.
You can leave both of them like that and see if you get
Okay.
same results. We had
Yeah.
Okay, yeah, it's the same. So that works too. Right. So say this was our univariate polynomial, right? And this is our claimed sum. We convert it to bytes, we just pass it. It absorbs, right? Then after it finishes absorbing, we now sample yes, the challenge. So does it make sense now?
yeah.
Are we sure?
So
So
this absorb can only take one argument, the one part as a time.
yeah, but you need to convert it to byte. You can decide to merge everything to one byte array and pass it at once. But that's like you.
Does it only take in string?
Huh?
Does it only take in string?
they absorb.
Yeah.
No, it takes in a byte array.
No, like
It-
yeah, bytes. Okay, if you want to convert like a vec to bytes, how would you like to do that? Let's say
So-
let's pass in a polynomial
you wanted to pass in a polynomial.
as bytes.
So you want to convert a vec to byte. That polynomial is made up of an array of field elements, right? So you want to be able to convert a field element to byte.
Yeah.
Basically, that is just like going through the array, converting all of them to bytes, and adding them into like one byte array. You just keep appending them, right? So that one now, like you can think of that as like serialization and deserialization, right? Anyhow you want to serialize your data, you should be able to deserialize it. But in this case, there's no need for us to start like implementing deserialize, right? But you can decide to serialize your data by just creating a new array and converting every element in the array to bytes and appending it to one byte. So in that situation, if you want to say you want to implement a deserialize, you already know the size of each element. It's a field element, right? And say a field element has a particular size. So you can just look through that array based on that size. You just pick, convert it back to a field element, pick, convert it back to a field element. I don't know if that makes sense.
Yeah, because this is what I'm looking at this for this string now. It's a
Yeah.
string already.
Yeah.
So you're converting to a byte, which is like that array.
Okay, so let's
for
say
it was like
let's say we want to use
you only need to do
FQ from 7, right? This is a field element, right? We want to convert it to.
so byte.
Should I be doing this? Isn't that S4? Okay, so basically you want to convert it to a field element. Hello, is everybody following?
Yeah.
Are we sure?
Yeah.
I know, like when we're dealing with the box, some people got carried away, right? Well, I hope we are back on track.
Yeah.
So I want to convert it to a field element. We can convert it to a big int first of all, right? We convert the field element to a big int and then convert the big int to bytes, either big Indian or little Indian. Okay, then we can call to vec. Okay. Expected a reference and found. Huh? Okay. Yeah, it's no. Just convert it to a slice. A slice is an array.
Yeah, so what I'm saying now. I wanted to send like polynomial like 0,1.
Yeah.
Yeah, it's already like in an array. So you just like change 0 and 1 to be bytes.
Yeah.
But then the array remains. So you don't need to do little bytes anymore. Because bytes have that array. Like
Yeah.
so it's
Yeah.
just the inside things you change.
Yeah.
And then you pass it to space.
So that makes sense, right?
Yeah.
Okay, so does this make sense? It's like everything we've done so far, does it make sense? Does anybody have any question?
So for this new one, you're trying to convert 7 to like
Yeah. We convert 7 to a byte
why did you have to convert to big things?
because on the field elements there is no direct method to go to byte. But a field element is still a big integer.
Yes.
You get, and on the big integers, there's a method to convert it to bytes. So we just convert from a field element to a big integer to bytes.
So what does this slice do?
Yeah, it returns a vector. So their slice just makes it an array. Yeah. Does it make sense?
So when the Kekak function squeezes out the byte, does that mean that it clears the state?
No, it doesn't clear.
So
There
why
is
is it-
finalize. Yeah?
It finalizes, yeah. So why is it the same after every?
No, it's always be the same because it's the same input, the same data. If you hash 1, you're always going to get the same thing.
Yeah, but that must mean that the state is clear at some point now. Because if it's not clear, if you call it again. Okay, after the function run.
Like after we call squeeze, we can now like let's say call squeeze again. Right? Is it what you mean? To see if the state was cleared or if it remained. Is it what you
I'm actually, yeah, you can try that, but I'm asking.
I think there's a way they keep track of like okay, this thing is the same input, so they always like add something else before sending the input. So it's always going to be the same. The same thing.
create? Yeah. So the states after we called squeeze, it did not mutate. Like it did not clear it off. You get? Because if it cleared it off, then here should probably have been like maybe all zeros or something. Like default. Does it make sense?
Yeah.
So we can still keep absorbing, right? And then squeeze again when we want to generate a random challenge. Then keep absorbing, then squeeze. Does it make sense? Are we sure? Okay. So I think that will be that for today, right? So hmm? The code.
Please, we need to
So
Okay.
It's good that
I'll people already have
okay.
people already have the link to that previous one, right? The one Wisdom used when he was implementing.
No.
He didn't share it.
We don't see.
No, it's there. It's basically in it. I'm doing this now.
Just be a guy, like, and you know when we get stuff, have references where you
The gist. I pray I remember.
and
Amen.
you don't do it
Close
now.
the
Don't do it now, please.
The notes. Okay, okay. But there's nothing here.
It's a lot. No, not the Fiat Shamir.
Okay, the previous
Subject,
one.
yesterday's
Okay, the
subject.
yesterday's note.
Because
Okay.
there's a step pattern.
Okay. I'll send it together with this video, then I'll also push and I'll tell Wisdom to make it public.
Please, can you just share?
Okay, no problem.
I have
No
a
problem.
question.
I'll do that.
If you wanted to test the transcript, not just test the hash. So you wanted to test that when you hashing what's it called? Maybe like hello world for example. You now want to assert that it's equal to the actual expected result. Now for you to get the first one you do all these ones. Then how do you now get the expected result that you want to assert it to in your test?
In your
Without
test.
going through the whole
You know, that was like you're generating random. There's no way you can know their output, right? So yeah, except you're the one passing. Yeah. So what you can do is, first of all, those places you're meant to be passing in a random challenge, you can pick a value and passing, just so that you can be able to test to be sure your code is working. Then after that, you can now change it to a random challenge.
I think
Does it make
for
sense?
this thing you're saying, building a tool around the window, like I'm just thinking, for testing purposes, just get your array of stuff or your byte and give it to that tool. It will
And to
give you an
generate
expected
tests.
hash. Then you can get that hash when you're writing your test. You assert that the hash you're getting from this guy is supposed to be hash that will give. Very nice.
Yeah. Yeah. I think like there are some public values available,
Yeah.
especially like when we like for KZG, like the trusted setup ceremony, there are some public powers of DAO listed available that if you want to like test your code, you can just use those public values. So I think something like that, but I don't know of any. Sure.
So eventually, for example, when the verifier gets the hash and wants to like take it back to get the challenge or a particular word, what does he use to backtrace it? When you get
No, the verifier doesn't get, like the verifier will call this function. So
so there's no way for me to get anyone give us those numbers. There's no way for me to get the words back from that number.
no.
No way at all.
You want to reverse a hash function. That's the only way. That's the only way. Like reversing a hash function. But the verifier, like the hello world and the other this thing, the verifier knows those things. Like, which of the hello world are you talking about?
Oh, I'm the one that is hello world.
Okay, you're the one that is hello world, right?
So for example, that boy now.
Yeah, the boy and the girl. The verifier knows the two of them. So the verifier can pass. The verifier is also going to call this absolve on the two of them, and the verifier is still going to call the squeeze. And in as much as it's the same values that the prover and the verifier pass in, they should get the same random challenge.
If he does not know the word, there's no way you can get the word back from that.
Exactly.
So
Exactly. No way.
it was one time and one word that was actually.
Yeah. So even if the prover wants to cheat and pass in one word, when the verifier is doing his own protocol, he's going to pass in the two, and it's going to fail, and the verifier will reject. You get?
Yeah.
So any other question? I think we're
So like this squeeze,
yeah.
the value, is it going to part of the proof?
The squeezed value, which is like the challenge.
Yes.
There's no need, right? Because the verifier can generate it.
But it's going to be sent to the prover. I mean, the prover is going to, yeah.
The prover will generate it, so the verifier will generate it. So there's no need to put it in the proof. Okay, so any other questions? No other question, right? So if at all you have any question, we're always still available. You can always ask. With that, I think we've come to the end of today. So it was nice meeting you. See you. Same time, same station tomorrow.